Hey guys, welcome to Related Rates Day 2. Um, Hopefully we have a decent idea of how to set these problems up and how implicit differentiation works with them. Um, there's just a few more situations that come up pretty regularly in these problems. We did a lot of like geometric stuff just to kind of get used to the techniques, but now we're going to talk about some other situations that appear. This one with the ladder is pretty common. So like imagine there's a ladder and it's leaning up against a house, and the bottom of the ladder is sliding away from the house, which means the top of the ladder is sliding down the house. And so the question is like, generally it's like how fast is the top moving or how fast is the bottom moving away? So there's questions like that. And the pictures look something like this. So like, it's kind of conceptual. There's the ground and there's the side of the house, right? And there's a ladder and it's like leaning up against the side of the house, something like this. Okay, so this is the side of the house and this is the ladder. And the top of the ladder is moving downward, and the bottom of the ladder is moving like away from the house. So the whole thing is like sliding down. Like if this is the way it is now, then like a second later it would look like this. Then a second later it would look like this. It's like sliding down. So one thing to remember about these is that this distance here, well, generally we call this y because it's an up and down distance. And this distance here, which we call x, is like those are changing as the ladder slides down, but the length of the ladder doesn't change. You can assume that. So that's constant. This is y, this is x. And this, so let's say in this problem, we want to like we want to draw pictures and name things. So this is this distance here is going to be 20. And it's never not going to be 20 in this problem because it says the extension ladder is 20 feet long. So this here is y, this distance is y, but this arrow, from my thinking, kind of represents a rate. This arrow is like indicating that the top of the ladder is falling down. So I would think about this arrow as like representing something like dy dt. Like this is how fast y is changing with respect to time. How is the height of the ladder, the top of the ladder changing? And this arrow here, which represents how fast the distance from the house to the ladder is changing, is like dx dt. And in this, so if this is the thing, this distance here is x, and this distance here, this distance here is y, and this distance here is x. And at any moment, those are constants, but in general, they're changing. So they tell me some other things. The ladder is 20 feet long. The bottom of the ladder is sliding away from the house. So that's this distance. And it's that their constant rate of 2 feet per second. So I would call that, I'd say dx dt equals 2 feet per second. And this 2 should be positive because the distance from here to here is increasing as time moves on. So this distance is getting bigger. So this is a positive 2. The question is, how quickly is the top of the ladder falling? So how fast, like how big is this number? At the exact moment, the base of the ladder is 12 feet away from the house. So they're asking me to find dy dt. And they're telling me to do that when the base of the ladder is 12 feet from the house. This is the base of the ladder, that's the house, so that's when x is 12. So remember, for the x's and the y's, I'm thinking about this triangle here as looking like this, where this is x and this is y and this is 20. And this you could call z or something or c or whatever, but it's always equal to 20. So I drew the picture, I named everything, write down what you're asked to find. I did that. That's right here, usually a rate. Write an equation that relates to variables. So the variables here are x and y. Those are the two things that I need to know, or that I don't know. They're changing as time is passing. And since the assumption, and it doesn't say this, the assumption is that the side of the house is that this is a right angle right here, which means that this is a right triangle, and I know a relationship between the two sides, the two legs of a right triangle, and a hypotenuse, namely the Pythagorean theorem. So I could say x squared plus y squared equals 20 squared. That's the Pythagorean theorem in relation to that little triangle I drew before with x and y. and 20. And this is good because I got a feeling if I differentiate with respect to time, I'm going to get a dx dt in this one and a dy dt in this one. And that's what I want because I know what those, I'm trying to find those things. So the next step is differentiate with respect to time. So I'll write out an extra step here I probably wouldn't normally write, just so we can see what's happening. So I differentiate both sides of the equation with respect to time. This equation right here. So the derivative with respect to time of x squared is 2x times dx dt. Again, I'm not going to say this for every problem. I'm going to assume you guys know how to do this a little bit now, but the derivative of something squared is 2 times the something times the derivative of the something. So the something here is x, and since x does not match t, it's 2x times dx dt. Implicit differentiation, the chain rule. Very similarly, the derivative of y squared is 2y times dy dt. And the derivative of 20 squared is the derivative of 400, which is always going to be equal to 0. So I've done this now. And then it says evaluate. That means like plug in all the things that we have and find the thing that we're looking for. So we were trying to find dy dt. We knew dx dt was 2. So that's going to be 2. But I also need, so this is what I'm trying to find. I know this equals 2. It said find it when x is 12, right? It said when the base of the ladder is 12 feet from the house. So I'm going to say 12 for this. But like now you have to find y. But that's not that tricky because you know that this is 12 and this is 20 and this is y. And if you know two sides of a right triangle, you know the third side. So I would say something like 12 squared plus y squared equals 20 squared. And I think if you do the math here, you get y equals 16. So this is 16. And then I plug everything in that I don't know, or that I know, and the only thing left, hopefully, is the thing that I'm looking for. So this x is 12, so it's 2 times 12 times 2, plug in all the numbers I got, plus 2 times 16 times dy dt equals 0. So this is 48 and this is 32. So I subtract 48 and I divide by 32. So dy dt is negative 48 over 32. Those both divide by 16, I think negative 3 over 2. And that should be, I think, feet per second. Let's remind myself. Yeah, derivatives are in feet per second in this one. And I'm glad this is negative. Because if you remember the picture, like the ladder's sliding down the house, so y is getting smaller as time passes, right? This is the height of the ladder, the height of the top of the ladder is getting less and less and less. And that's good. It's negative because y is decreasing, and that makes me happy. That's the way it should be. So that's a problem. It's not that uncommon. And I don't think there's anything super different or tricky about that one particularly. It's just you have to know how to set up the picture and be able to identify the variables and draw the picture. Sorry, not draw the picture. You have to draw the picture, assign variables in an intelligent way, and then write an equation that relates to variables. That to me is the harder part. Once you guys know how to do implicit differentiation, this step isn't that bad. It's like this step. It's the first two parts of these that tend to trip you guys up. So I'm gonna do a couple more examples here with some different situations. There's one here with an angle. That's a little trickier. I may not do this one, but I'm for sure going to do the one with the cone because those are pretty hard. So I'll do those in the next video. Bye.